my other class, so my throat's a little bit raw. Okay. Today we are going to have the first of our lectures on an agent-based model. Agent-based modeling is the topic we'll be covering for most of the following semester. We will be spending quite a bit of time discussing multi-model issues such as calibration, sensitivity analysis, dealing with stochastics, etc. But agent-based modeling is going to be the approach we spend the most time on. And I want to give some comments on motivations for this. Why agent-based modeling in particular? We've seen quite a bit of emphasis on system dynamics models and viewing them through a dynamical systems lens, looking at their behavior in state space, etc. I want to talk now about agent-based modeling in contrast to that. And so let's take stock a little bit, step back. We've been dealing with system dynamics modeling, which is a feedback-centric process. Focuses on feedbacks and accumulations in the form of stocks. And it spans qualitative and quantitative methods. You saw that in problem set 1 where you have causal loop diagrams on the one hand and stock and flow models. And as you're seeing in problem set 2, it supports rich mathematical analysis. We saw that last time. And typically the models here are small enough that we can use them interactively. You'll find that VenSim has a mode, and I'd suggest you folks explore it if you haven't already, called Synthesim mode. And basically what this allows you to do in this mode is to run model variables interactively. I guess I don't have a VenSim up right now, but you can run the model interactively with different assumptions about variables in a highly interactive fashion. This can allow you to explore particular behavior modes. So you could see here that we have this kind of different dynamics, and then I could adjust parameter values here. And maybe what I'll do is I'll create a baseline for this model, and then I'll create a and it's actually running it there, and then I'll create an alternative. And then what I can actually do is to adjust these parameter values and see, for example, how it ends up impacting the dynamics. So, for example, I could change to a longer duration of illness, and it will update. And in this model is actually a quite slow one because it's integrating it at a very fine time step. But if we were to go to this, and if we were dealing with a model which had a much coarser time step, this sort of run is almost instantaneous, and you could literally drag these sort of things and see how the modes of the system. You'll see the blue one kind of moving around there interactively. This is a sort of type of interaction that it's very fruitful for learning to be able to do and to observe the results. And in fact, we saw through mathematical analysis we could actually reason more broadly about the general modes of behavior of the system over a wide variety of parameter values. That's very useful. So system dynamics modeling and dynamical systems approaches that come with it are very powerful approaches. Agent-based modeling will be able to leverage some of those insights, but presents a far more fine-grained characterization of a system. So in system dynamics, we are interested in the emergent patterns that come about through interactions of stocks and flows. Those are sort of what's driving the emergent behavior. Behavior that can't be explained by any one stock or flow in isolation. Instead comes about because of the interactions, the model structure in terms of stocks, flows, and feedback loops. In agent-based modeling, the dynamics and the emergence comes about because of interactions between individual agents. Okay? And we'll see that these agents can be at different levels of a population. They can be at in other words, in a multi-scale model, we might have individual agents, we might have neighborhoods, which are themselves perhaps not agents, but collections of agents. Then we might have cities, which have some agency because there's governments associated with them, etc. And there's some actions undertaken at that level per se, similarly with schools, etc. So agent-based modeling captures interaction between different actors within a population, captures individual level actor trajectories and histories, which it turns out to be quite important, in contrast to the kind of cross-sectional depictions possible in system dynamics models. It gracefully represents network connections and nesting contexts. It captures heterogeneity in a much richer sort of way, and allows for really detailed policy planning. So planning very, very detailed policies that might involve learning, for example, as processes. We'll later see discrete event simulation, which simulates flows of individuals through processes and captures resource use. So here we're kind of contrasting on the one hand, on the left-hand side here, a system dynamics model, on the right-hand side, an agent-based model, perhaps for the same population. Something that we represented as kind of a random mixing between individuals, reasoning about the average number of people you come into contact with per day, we may represent as an explicit network over here in the agent-based modeling context. And this network may be static, or we do a lot of work here using data collected from smartphones where the networks are extremely dynamic. Maybe we have a different network every 5 minutes. We represent people's contact patterns as they evolve throughout the day. We can capture these individuals in many ways. And one of the things I talked with someone about in the room was the fact that turns out you can do agent-based modeling or individual-based modeling, I guess I should say, to be maybe more specific about the term, in something like MATLAB. You can actually do individual-based modeling in Vensim. You simply have each stock subscripted by population member. So you can have a number of infected cells for person 0, for person 1, for person 2. It's like having a Y sub I, where I is the population member. Agent-based models are different from this. They're a type of individual-based modeling where we encapsulate the agent as a software object, as an instance of a class. We wrap up in a single object the individual's characteristics and the methods that affect them. Okay? That's quite unlike doing something in MATLAB where each agent is defined, as this element of this array, this corresponding element of this other array, this corresponding element of this other array, where each array represents some vector of state variables for each successive agent. That's what I was talking about doing in Vensim as well. Here, we have agents represented as objects, and they interact as objects, and they nest as objects. So we have references to agents, say, who live in a given neighborhood, and that kind of mirrors sort of the organization in the external world. Turns out that's not an obvious thing, but it's a real advantage. And objects provide a really convenient abstraction for this. It's one of the reasons we use object-oriented software techniques, why they're so popular. In contrast to what we've seen so far with system dynamics models, agent-based models currently require writing in conventional programming languages. Over time, that's evolving. You see techniques like packages like Venn or any logic to do more and more to make it declarative, but there's still quite a bit of code being written. And it turns out we can follow a system dynamics process in terms of analysis, but so it's a very similar sort of analysis we can conduct, but the model's at a lower level of abstraction. So what do we have in these models? We have one or more populations composed of individual agents, and each agent will be associated with some state, some parameters, and some rules for interaction. Okay? This is in contrast to, well, I'll get to that in a moment, but this is in contrast to a situation where we disaggregated the whole population into categories according to state earlier. These individuals embedding in one or more environments, sometimes local environments and global environments, and typically they have localized perception. They see the area, or they sense the area right around them. They impact things in the area right around them. Einstein famously commented that in response to the EPR experiment, that he does not believe in spooky things at a distance. He you know, when taken a choice, he also made a comment, God doesn't play dice with the universe. But what you'll find among a lot of physicists, and Einstein, as I understand it, was no exception, was that they're much more willing to believe in a somewhat stochastic universe with quantum uncertainties and so on than they were with non-local interactions. Interactions that don't involve locality, that occur suddenly across a very, very wide area. And here, within an agent-based model, we can represent that locality. Sometimes we represent it in space, and any logic supports 2D and 3D model for capturing space. Sometimes we represent it in a network sort of way. So I affect the neighboring people in a network, and they affect their neighboring people, etc. And so I'm connected with people in a network, some of them at further physical distance, maybe a phone or Skype or whatever, and some people maybe more localized. But in any case, we can capture localized impact, not necessarily spatially, but topologically. And here the agents will communicate via messaging and or flows. And this is flows as in stocks of flows. We'll see that. That's a possible mechanism. So they're in these environments. And here, aggregate behavior will be emergent, but it will also be emergent over space and over across networks. Okay. Well, we noted this, that here we're capturing agents as objects, and it turns out this facilitates convenient representation of nesting of relationships, such as individuals and neighborhoods, and networked relationships. The fact that people are in networks. So this is a slide I showed earlier, I think, but it's something worth reflecting on. So we've seen quite a bit of aggregate stock and flow models. Here we're, and let me make a high-level statement, and I really want you to remember this, okay? This is very important. So aggregate models, stock and flow models, are organized according to state, okay? We subdivide the population according to state, and then the data we collect for each of those subunits, each of the subcategories of state, is a count associated with the number of people with that state, right? Or with that characteristic. This state should really be properties and state, characteristics and state. In agent-based modeling, we instead organize the model. We don't subdivide according to state. We subdivide according to person, or according to individual. In short, instead of organizing according to state like we do with aggregate modeling, we organize it according to individual distinction, individual person in the population, or individual actor. And then for each of those actors, we keep track of their state, their characteristics. Okay? So it's kind of like one is orthogonal to the other, organized according to state, counting the number in that state for aggregate modeling, for agent-based modeling, organizing according to individual, and then for each individual recording the state. Okay, so here we had our model broken into 3 categories, subdivided according to state, and each stock counts the number associated. And the state for different units of analysis are found at stocks and flows at the same levels of the model, in the sense that we may have, for example, a variable that may be like the total population size, and it's simply another variable in this model. It's not any sort of at a higher level explicitly or visually. It's just another variable in the model. And we might have, susceptibles in city 1, susceptibles and infectives in city 1, recovereds in city 1, susceptibles in city 2, infectives, etc. And they'd be just different variables within the model, and we could sum them up, and we'd find them, at the same level of variable. And the relationships between the units is implicit in the data. For example, we might have a connectivity matrix. By contrast, in agent-based modeling, we have individuals, and those individuals are the kind of unit of organization. And each individual then maintains their own state. And it might be with one state chart, and might be with several state charts. Orthogonal state charts, essentially. Maybe interacting some, but more or less independent of one another. And here, the nested or networked relationship among these sort of units of analysis mirror those in the world. So if we have nesting, in the real world with sort of people being located in neighborhoods, within our model, the references to those people will be located in the neighborhood class, an instance of the neighborhood class. So we have that sort of nesting mirrored within the structure of our model. Now, very importantly, within a system dynamics model, people are subdivided according to discrete state, right, or discrete characteristics. So we had people divided up into categories. That was how we captured heterogeneity as well. If we wanted males and females, we'd have male susceptible and female susceptible. But it was always a discrete sort of characterization. Even if we wanted to capture people of different ages, we would do so in age categories. So we'd have infectives of age 0 to 4, 5 to 9, 10 through 14, etc. By contrast, within an agent-based model, we have the option of doing things in a discrete way, and we often will for gender, ethnicity, categories, categorical infection status. But we'll often make use of continuous categories as well. Age, for example, elements of body composition, someone's metabolic rate, their birth weight. These need not be discrete categories. We don't have to force fit our continuous categories into a set of discrete divisions here. We have the option within our agents of using discrete breakdowns, as we did here, SIR, or we have the option of recording continuous things and having those continuous things evolve as such, which is a powerful component. And as we'll actually see, we may often choose to use stocks and flows to describe their evolution at a continuous level. So there we would have an individual's state being continuous, and maybe it's their level of infection or something like that, the level of virus particles in them, which we can essentially treat as continuous, and it varies according to stocks and flows over time, so it's continuous in time. What's notable here is that some of these feedbacks that we saw at an aggregate level within a system dynamics model, let's suppose we wanted to diagram nicotine exposure. So, people are exposed to nicotine, it leads to greater severity of nicotine addiction, likely to smoking, and new nicotine exposure. This might be a feedback which operates at an individual level. And here we might represent that feedback in an agent-based model and an agent-based model in a feedback at an individual level as well. By contrast, there's some other feedbacks in an aggregate model. For example, if we had a stock of smokers, maybe the more smokers there are, the greater the perceived desirability of smoking, and therefore the faster the rate of people uptaking smoking. Very stylized, and I don't want to argue whether or not this is true. But we could have a model where this is captured. Similar arguments have been advanced for obesity, for example, that as weight levels go up, people's sense of what a normal weight is rises with that. They look at the people around them, they kind of judge what sort of rate they're shooting for, and so people's target weights rise, and then it leads to sort of this ambient rise. And that's in effect operating at the aggregate level here. What's notable here, though, is that this effect, even though it's a feedback at this aggregate level, when we represent it at an individual level, there's no feedback. There's no feedback where it comes back around and affects an individual. In this one, there is a feedback, and yet we'd represent it in the aggregate model in a similar fashion. In this case, in the aggregate model, another sort of first-order system here, a reinforcing feedback, yet another reinforcing feedback. It disappears as a feedback at the individual level. Instead, it's an interaction between agents. Here's Johnny's father, and he's influencing Johnny, and Johnny, because of that, takes up smoking, and he influences his friend Timmy, who is pressed with cigarettes by Johnny. So here we have this feedback loop, which is at an individual level not evident. It's a feedback loop at an aggregate level. So just be aware that when we take an aggregate level model and we translate it to the individual level, we don't necessarily just one-to-one map the feedbacks onto individual level feedback. Sometimes they are, sometimes they aren't. And this highlights one of the ambiguities present in aggregate system dynamics models as to whether this is an individual level feedback or just a feedback that affects sort of a stock of different people over time. That is left unsaid. And in fact, one of the things we'll see in a system dynamics model is it doesn't typically allow you to reason effectively about the trajectories of individuals. It's more about cross-sectional depictions. How many people are there in each category over time, not whether they are the same people over time. It doesn't allow you to trace an individual trajectory like we'll be able to do in an agent-based model. Okay, so here in an agent-based model, we will see system dynamics sometimes. Here's, for example, an agent-based model where we have stocks and flows within an individual depicted in any logic stock and flow notation. This is their implementation of system dynamics. But we'll often have discrete states like this with state charts. Individuals will often be depicted in networks. We may place them in regular environments, spatial environments like we saw the first day, or irregular environments like this hospital setting where they may move around. And we may have them moving in the context of spatially explicit GIS type of systems where they move through geographic space in important ways. Here, emergent behavior within stock and flow models. We saw very powerful emergent behavior, and you'll see it. There's some very interesting emergent behavior at a stock and flow level, an aggregate level within problem set 2. But in agent-based models, we see this not only at the level of aggregate stocks and flows. We can aggregate up from an individual-based model, an agent-based model, to an aggregate model. We can talk about stocks and flows in this model. We can ask how many people have gotten infected in the past day. We can ask how many people are currently infected. We can always do that by going up from the bottom. But the interesting thing is that the emergence within agent-based models will occur not only at those levels of stocks and flows, although it will occur in interesting ways there, but between agents, and most notably in terms of some physical or some spatial phenomenon or phenomena in terms of networks. So we'll see some quite interesting emergent behavior in both those areas. So we saw some of this the first day. This is not a pattern that you'd see readily in a system dynamics model. What you'd see instead is kind of a build-up in the number of people. So you'd see something like this. If we were to look at this in a system dynamics model, or at an aggregate an aggregate stock and flow level, and we were looking at the stock of people infected, it would rise and then it would decline. What we wouldn't see is this. What we wouldn't see is this sort of mapping spatially that can be very, very important. And if we're building a model that we want to capture salient patterns in the external world, often it's valuable to work with a modeling technique that allows us to represent this sort of phenomena, this sort of phenomenology, and to be able to reason about it. I also mentioned ABMs can be set up to have multiple levels of scale or context as present. And often this emergent behavior can be strikingly different according to the level of scale. So look at the emergent behavior for the aggregate model versus at the individual level versus at the kind of mesoscopic level where we have multiple individuals. So you'll be a sort of multi-level modeling. Okay, so I noted we have emergence in both types. Agent-based modeling particularly emphasizes multi-level emergence, how distinctive patterns can emerge at different levels of the system. And this type of behavior can change significantly with changes in structure and parameter values. So what are the trade-offs between these things? Well, one important trade-off is that aggregate models, as I demonstrated earlier, have much higher performance, and they're often easier to construct. There's fewer moving parts, so they're easier to calibrate. There's fewer parameters that need to be adjusted. They're often easier to collect data for, although that's not always the case, and to formally analyze there where it's at. We don't know how to analyze right now agent-based models. That's the strict truth. Our mathematics is not yet advanced to the point where we can readily do the sort of rich analysis with agent-based models that we can with aggregate models. We're just not there yet. There's some techniques which are being applied, which have relevance, but we're not nearly as far along. And often aggregate models, you can come to more quick understanding of kind of what's going on because there are fewer moving parts. There's less pronounced stochastic, so you don't have to run what are called Monte Carlo ensembles. This would be running the model again and again and again and again because each time it yields a slightly different result. We'll see how that works. We'll see some of the mathematics associated, statistics associated with it. And they're often quicker to construct, aggregate models. Individual-based models, however, have some incredibly compelling strengths as well. They have better fidelity to many dynamics. We can characterize things more precisely. For example, memory full processes, situations where our likelihood of leaving a stock per unit time varies with how long we've spent in that stock. Something that we can only do in a crude way in an aggregate model by stringing together chains of stocks. They provide stronger support for highly detailed policy planning because we can represent very detailed phenomena. They have greater, it turns out that we can calibrate individual-based models to detailed level information on individual progression. A stock and flow model, ladies and gentlemen, gives you a set over time of a cross-sectional depiction. Let me give an example of this on the board. One thing we didn't talk about in this class, and I regret not being able to cover it, is these very interesting models that are called SIRS models. Okay, these are models where we have some amount of immunity, but it's not persistent, and so eventually you go back to the susceptible stock. And there's many conditions like this. Chlamydia, gonorrhea are two ones in the sexually transmitted infection front. You could argue that flu is kind of like that. You get infected, like I did last week. You go through your downtime, body aches, chills, coughs, sneezes. Good description of me over the weekend. You get over it, and hopefully that means I'm pretty much immune for the next year or so. Until the virus mutates some more. SIRS models are really interesting. We can get these quite fascinating fluctuations in dynamics and so on. But what a stock and flow model won't tell you what that is. How many people are getting infected more than one time? What's the distribution of times, number of times they've gotten infected? Some of those questions can actually be posed and answered, but they're very difficult to get insight into. And there's some questions that really can't effectively answer. Fundamentally, we can't trace individuals among these categories. All we can get is a sense of how many people are in the S state over time, I over R. We can't ask, is it the same individual as there now who was there 20 time units ago? How many people are going through this many, more than 10 times in the course of the simulation? Instead, all we deal with is kind of averages. The number that are there. We abstract away from who it is. By contrast, in an agent-based model, we do have that information. And we can match, when we have information from the external world that gives us individual progression, we can match to it. Turns out individual-based models will be able to provide a much stronger point for looking at heterogeneity, sort of a highly varying population, and they'll allow us to examine finer grained consequences, like spread across the network or spread across space, geography, etc. And it turns out that they just provide simpler mechanism, a description of some causal mechanisms. A lot of people find it simpler to reason about things at an individual level. Rather than reasoning about these sort of averages, well, on average, I see these many people per day. For the whole population, this fraction's infected, so that probably means I see about this many people per day who are infected. Instead, we just deal with networks. We deal with networks and connectivity and contact patterns between people that are represented person to person. So here's some key needs motivating this sort of modeling. We have to calibrate against information on individual trajectory. We need to capture progression agents along multiple pathways, for example, diabetes, TB, cancer, etc. We wish to characterize learning by agents over time, so how agents learn, change their attitudes. We have to capture localized perception among agents. They can only see those in close proximity. Or if we're seeking to intervene in or change points in a network, for example, at particular points within a network. Perhaps we're hoping to change the structure of the network, and we want to reason how that will affect the overall behavior of the system. Suppose we want to seek distinct interventions for for different categories of people, for example, or we want to see what is the impact of intervention across many categories. Sometimes we just know information about the behavior at an individual level much better than at an aggregate level. Sometimes we want to experiment, is this aspect of heterogeneity important? If we add in a distinction by sex, or a distinction by ethnicity, or a distinction by age, how much of a difference will that make? To do that in an aggregate model requires subscripting the entire model, often, or a large fraction of it. Here we can do it just by adding one property to an agent, and very readily modifying the model in a very localized fashion. Sometimes some stakeholders want to reason about things in an individual model, and one of the most compelling things is the desire to examine things at multiple scales. Why would you still use aggregate model? You want to execute it quickly, describe system behavior across all possible values, use mathematical tools such as control theory, use of things like eigenvalue elasticity analyses to understand what feedback loops are operating right now. You want to calibrate it to a lot of historical data. Often that's easier to do here. Perhaps stakeholders want to work at a higher level description. If the behavior of different subgroups differs only in degree, or you have no recourse to software engineering. Ladies and gentlemen, this is one of the big reasons I'm teaching this course. There are far too few people to do agent modeling. Lots of people want to do it, and few people that can do it. Especially few people who have the depth of computer science background. There is desperate need for folks trained in computer science who can do this sort of modeling, and it's a perfect mixture of skill sets. And finally, if you have lack of detailed knowledge of network structure or individual level behavior, that can really make it difficult. So here's some limitations, inability to mathematically analyze them. We'll see that some runs can take a very long time, particularly when we need to run an ensemble, need to run the system many, many times, say 50 times, to generalize about its behavior. That time could have been devoted to something else. It could have been devoted to enriching an aggregate model, for example. Sometimes calibrating yields no unique interpretations. There's so many moving parts that there's no one unique calibration. We have some ways of dealing with that, but it's one of the challenges. It's an underdetermined system, to use a term some of you may have encountered before. It's not a problem for you, but for many people, software engineering talent is not available for it. Achieving model transparency will be a challenge. We're going to have big models that are much bigger than our system dynamics models. How do we make those easy for people to understand? How do we specify them in a transparent fashion? How do we publish them and share them? Traditionally, it's been a modeling process hasn't been as well spelled out, sometimes building individual level models is premature because we don't have the theory as to what's going on, and it leads to a lot of speculation. I argue that these techniques should be used together, that each component of the elephant, and that each type of systems modeling has different core questions. It's not just that they answer it in different formalisms. They do, and there are interesting overlaps between different trade-offs. But fundamentally, the questions asked of system dynamics are different than the questions asked of agent-based modeling. System dynamics is often focused more on stakeholder buy-in and changing people's mental models, whereas agent-based modeling is much more focused on quantitative model output. Quantitative insights from running these models, more realistic models often, although not always. It has differences in the problems that they can address. The different types of modeling can be highly complementary and synergistics, and we'll be talking within this class late in it about combining these together in really rich ways. And those are some of the most powerful ways. And AnyLogic's the only platform that makes that really, really easy. So these are some early comments on agent-based modeling. Are there any questions on these before we dive into AnyLogic as a framework? And I'm going to take you on a sort of lightning tour of a bunch of features that you can then explore on your own. Any questions about agent-based modeling and aggregate modeling? Nothing? Okay.